All right, so now let's begin our review on work and energy. Okay, so this is a huge part of AP Physics C, really important part. So let's just remember, how do we calculate work? Remember, the force has to be perpendicular to the displacement. We do that dot product, or we do an integral of it if the force is not constant. But remember, the key idea, don't worry about so much the formulas, but just remember the general structures that the force has to be in the same direction, parallel to the displacement, and then there will be work. If it's perpendicular, doesn't do any work there. So when we compute work, we got to draw that free body diagram correctly. We have to understand the direction of the displacement, and then we either do the integral or that product. And the key part is that work causes a change in energy. So work is a scalar quantity, can be positive or negative. We cause a change in energy in the system. If there's no external work, that means if the work is zero, then we say the change in energy is zero, and that is when we apply conservation of energy. So a key part, this is our key equation for this unit, and work being zero implies the change in energy is zero. So that is conservation of energy. So now there are different forms of energy depending on our system. Kinetic energy is the most basic one. It's 1/2 mv squared is the energy of motion. Anytime anything moves, it has kinetic energy. Gravitational potential energy, near the surface of the Earth, where we assume the gravity is about constant, right? From Newton's law from the previous unit. When we're near the surface of the Earth, or the gravity is about constant, potential energy from gravity is mgh. We have to include the Earth as part of the system, right? So if the Earth is part of the system, then gravitational potential energy comes into that energy portion of that equation and not work anymore, right? So we ignore work when we include Earth as part of our system. Potential energy is relative to a specific height. So you need to put a reference height where h is equal to 0, and anything above that reference height is positive potential energy. Anything below that reference height is negative potential energy. Okay, and so the total energy is always the sum of all the energies in the system. When we do far from the Earth, okay, and then we talk about gravitational potential energy, we use this form. Now this one, the reference height is h equals infinity. At infinite distance, the potential energy is 0. So the reason there's a negative sign, and a lot of people forget this negative sign, the reason the potential energy is negative is because we assume the reference height is infinite distance away. Because when you're talking about planets and things like that, what is h? There's no universal standard. So we say infinite distance away is where the potential energy is 0. And anything closer than that is going to be, or under that line, is negative potential energy. So that's why gravitational potential energy formula has negative when we're talking about planets or far from the surface of the energy. Now, sometimes when you're calculating potential energy of a system and there's more than just two objects, there's just two objects, you use this formula. But if there's like 3 or 4 objects, every pair of objects in that system has potential energy. So when you have 3 objects, you have to do the potential energy of every pair, and there's 3 pairs in there. So there's that. And then spring potential energy is if the spring is in the system, then you have the 1/2 kx squared. It's very similar to Hooke's law. You can actually do it from work. The integral of kx, right, dx is 1/2 kx squared. That's kind of a little bit where that potential energy comes from. But basically, anytime the spring is stretched or compressed a certain distance, then it contains some energy stored in it. So like x is how much you've stretched or compressed it relative to its relaxed length, just like Hooke's law. Okay. And then power is the rate of change of the work or change in energy. So power is the derivative of the work. And at a moment in time, because work, you can think of it as F, times the displacement. If you take the derivative of this with respect to time, this will be the power. If the force is constant, then it's just the derivative of the displacement, which is the velocity. So this is if F is constant. But it actually applies in a short amount of time as well. Like at a moment in time, instantaneously, even though the force might not be constant, but like if the force at that moment, at a particular moment in time, if that force really isn't changing very much, then we can say the power is related to the force times the velocity. So let's go through the overall problem solving process, right? So we want to identify the system. Right? Are we including the object? Are we including the Earth? Is there a spring? If there's Earth and spring, identifying the system identifies what forms of energy to be included in our calculation for energy. Okay, so if we just have an object, we just have kinetic energy. If we include the Earth, we include gravitational potential, include the spring, include spring potential energy. If you have all three, you're going to include all three forms of energy. You want to draw a free body diagram of the system. And the whole purpose of this, these two go together, is to calculate the work, right? We're doing work as change in energy. We want to calculate the work. We want to calculate the change in energy. So all of these steps are about calculate. This is about calculating work. This is about calculating the change in energy. And then this is just applying work is the change in energy. Now remember, you still want to do all these steps. So draw that free body diagram, determine if it does any work based on the work calculations, right? With that dot product, is the force perpendicular to the displacement? Is it parallel? Is it internal to the system? That kind of thing. We calculate the work, calculate the initial and final, and apply energy, which might be conservation of energy if the work is zero. Okay, so that's our general problem-solving process. So let's kind of go through this. So block is released from rest and slides down a track with negligible friction, descending a vertical distance 5 meters from initial position to point P, as shown in the figure. Block then slides on a horizontal surface with a coefficient of kinetic friction mu k. And how far does the block slide before coming to rest? So over here, he's going to come to a velocity rest, and we want to know how long he's going to go there. So now, first of all, what's our system, right? What's our system? We want to think about, because there's a change in height, we're going to do the Earth, and we're gonna do the block, right? Okay, cool. That's the first step. Now we want to draw our free body diagram. We wanted to establish if any of them are going to do any work. So you might have to do a few different free body diagrams. So here you might have gravity downwards, and then you have a normal force, but there's no friction here. And then down over here, you're gonna have gravity, you're gonna have a normal force, and you're gonna have friction. Okay. Now, any moment in time, the displacement down the ramp is like this way. So because it's perpendicular to the normal force doesn't do any work because it's perpendicular to the displacement. Gravity doesn't do any work because it's part of our system. We've included the Earth in our system, so we don't include any work. So here, the work is zero. What about over here? You have displacement to the right, so the normal force, again, perpendicular to the displacement, doesn't do any work. Gravity, perpendicular to the displacement, and also part of our system, doesn't do any work. But friction's going to do some work here. So the only work we're going to have is negative work by friction, because it's pointing opposite direction of the displacement, times how far it's going to travel, and that's a constant force, and that's our work expression. Right? Now that's equal to negative, because it's kinetic friction, so it's just mu k normal force times the displacement. And if you look at our free body diagram, because the acceleration is only horizontal, the normal force is going to equal mg, right? Okay, now we want to talk about the energy that we start here. Now here the velocity is zero, so there's no kinetic energy, but there's some gravitational potential energy. Where are we going to say our reference height? Might as well say the ground is our reference height. My suggestion is always the lowest point. That is where our reference height is going to be, the lowest point in the motion. So that's going to be mgh, right? And that's 5. And then at the end here, we're not going to have any energy left, right? Because we have no kinetic energy, because the velocity is zero when we come to a rest. And also, the height is at 0, so there's no potential energy. So this is 0. So then we're going to have negative mu k mg delta x. Now we're doing work is change in energy. The final energy, which is 0, minus the initial energy. Okay, so that's just 0. The negatives can cancel, and the mg's can cancel. So you get this mu k times delta x is equal to h. And so the distance we want to travel from there to there is going to be h over mu k. And that's going to be 5 divided by 0.2. That's going to be 10 meters. That's going to be c. So that's the whole process, right, when we're doing a problem like that. All right, student lifts a ball straight up at constant speed. So constant speed means the acceleration is 0, right? The energy bar diagrams represent the gravitational potential energy of the ball-Earth system. They've already told you what the system, and the kinetic energy of the ball at time t equals t0, and a later time t equals tf. Which of the following energy bar diagrams collectively represents the change in mechanical energy of the ball-Earth system for the time interval for here. So system, right, is going to be the ball plus the Earth. Right, that's our process. We want to draw a free body diagram. So he lifts the ball straight upwards, and then so we have gravity, and then he's lifting it upwards from his hand. Right, he's lifting it up, and these two forces are equal because we know the acceleration is 0. Right, because that's the constant speed. And so what correctly represents the change in mechanical energy of the system for the time interval from T to TF. So what's the system? Is there any work? Let's look. So we're going to lift this thing up, right? And so we're going to think about, does gravity do any work? No, because it's part of our system. So we consider it part of potential energy. But this guy's going to do work. So the work is going to be from the hand times the displacement. And that's going to give you, and how much energy do we start with? Well, we just start with the K here. So like this is our initial energy. This is our final energy. And so the work, the F hand times the displacement, is going to be how much energy we have minus how much we started with. Well, how much energy do we have at the end? Again, the potential and the kinetic energy. You have like 1, 2, 3, and 1. So it's like 4 of those, 4 bars. And then you have 1 bar here. So it's 3 bars, right? The work by the hand is going to give that change in the kinetic energy. And so that's going to be 3 bars, C. 1, 2, 3, right? So we look up at the change in the energy. Okay. 2 small identical blocks, block 1, block 2, are dropped from rest at different heights on the horizontal floor. Block 1 has speed v1 immediately before hitting the floor. Block 2 has speed 2v. Okay, so different heights. So identical. This is the same block. This is going to drop. It's going to have v1 before hitting the floor. And then this is some different height. Could be greater. It's going to have a mass. And then down here, it's going to be going v2, or it's going to have 2v1 before hitting the floor. Work done by gravity as it falls is w1. What is the work done by gravity? Block 2 as it falls. So what we think about now, the system, we're not including the Earth because we're doing work done by gravity. System is just the block, right? So if we draw our free body diagram, gravity, it's the only thing doing work. It's only force, so the work is mg times the height here, right? That distance. So that's the work. That's the work done by gravity. And that's going to equal the final energy minus the initial energy. Now, what is the initial energy? We're only considering kinetic energy. Now, because we are dropped from rest, the velocity is 0 here, right? We don't have any initial kinetic energy. This is 0. So this is just going to be the final energy, which is 1/2 mv1 squared. So the work done by 1, okay, don't have to worry about the height, just the work overall, is just equal to how much kinetic energy we have in the, and then W2 is how much kinetic energy we have down here. It's m times 2v1 squared. And so that's going to be 1/2 m times 4 v1 squared, which is 4 times 1/2 mv1 squared. So it's going to be 4 times the amount of work, because it's going to have 4 times the amount of kinetic energy, right? Just looking at the work as that change in energy. So work 2 is going to be 4 W1. So it's going to be D here. Okay. All right. Let's take a look at some free response questions. So a small block of mass M. And the derivations I've intended to do is they're all symbolic, just like the other ones. Focus on the symbolic derivations and focus on some pretty hard ones. I think the practice test FRQs are actually pretty difficult. So I want to give you guys challenging ones. So a small block of mass M is placed on rest on top of a smooth frictionless sphere radius r as shown. The block is released and slides down the surface of the sphere. At some point, the block loses contact with the sphere of the surface. Okay, so he's gonna start from rest. He's gonna slide down. Eventually, he's just gonna kind of fall off at some point. Derive an expression for the speed of the block as a function of its vertical height below the top of the sphere. So what they're saying here is, let's call this h. Okay. Express your answer in terms of m, h, r, and physical constants. So we want to know the speed. So we might want to do looking at conservation of energy here, or at least the work energy process, just because the forces are going to be changing, right? So it's going to be hard to do kinematics because the forces are always going to be changing. So first step is, what is our system? Because there's a change in height, we want to include the Earth. We're going to do the Earth plus the block. Now we want to draw our free body diagram. So our free body diagram at any moment in time is you're going to have gravity, and you're going to have a normal force from that surface. Nothing else is touching it, and there's no friction, so we're done with our free body diagram. Now, the displacement, this is a little tricky. The displacement at any moment in time is the direction of the motion perpendicular to the normal force, so the normal force doesn't do any work. And because we included the Earth, gravity doesn't do any work, so the work ultimately is 0. So that means we can do conservation of energy. So we're going to look at the energy here, and we're going to call this h. So let's set the lowest point in the as the lowest point in the motion. Like here, I want to know how fast he's going. So the lowest point in the motion is going to be h. So the initial energy is going to be no kinetic energy up here. This is the start of the motion. There's gravitational potential energy, And then finally, down here, we have some kinetic energy and no gravitational potential energy because I made the height h equals 0. There. So we're going to set those equal to each other. M's. So then you get the V is going to be square root of 2gh. Okay? So that one's hopefully pretty straightforward. Let the angle theta represent the angular position of the block measured from the top of the sphere with 0 degrees at the top. Derive an expression for the normal force exerted by the surface of the sphere and the block as a function of theta. Express your answer. So here, we're going to do our free body diagram. Okay, so we have gravity. We have our normal force. And now the acceleration, this is our forces problem. Now, which way is the acceleration going to be? Well, we have acceleration because it's moving in a circular path, and it's also speeding up. We have an acceleration, centripetal acceleration pointing this way, and you probably have some tangential acceleration this way because it is going faster and faster. So you have two components of acceleration, but probably focus on decomposing mg into this part, mg, and then this angle is theta. This is going to be mg cosine theta, and this is mg sine theta, right? And so then if I do F net equals ma, in the radial direction, we'll say this direction is positive. Why is that direction positive? Because that's the direction of the centripetal acceleration. So that's going to be mg cosine theta is that direction. Normal force is out of that away, and that's going to equal mv squared over r. Okay, sorry, centripetal acceleration, right? So we can solve for the normal force. It's going to be mg cosine theta minus mv squared over r. We can't use v, but we have the speed here. Well, okay, so now we have to think about, okay, so we know v is square root of 2gh, but I'm not allowed to use the height either, so I got to use the theta. So now I have to go back to this picture and think about how do I figure out what this h is in terms of the theta, right? Because that's where I'm stuck on. I got to do it in terms of the theta here. So let's talk about, let me redraw this line again. We want to know what this guy is. That way I can put everything in terms of just theta. I can get rid of the h. Because right now if I put that into there, it's going to be mg cosine theta minus m2gh over r equals fn. The h is the problem, right? So I need the h in terms of theta. We know that this is r and this is r. And if you look at this right triangle, this distance here to here is r cosine theta. And this whole distance is r, so this distance is r minus r cosine theta. Right? So you got to think about that. Pause it. Think about it if you need a moment. But then the h is good. So this is going to be square root of 2g times r minus r cosine theta. Okay, so we can plug that in for, this is our v squared, right? So plugging that into, so v squared is going to be 2g r minus r cosine theta. Plug that into there, we get mg cosine theta minus this thing, 2g r minus r cosine theta over r. You can cancel out those r's. This would be 1 minus 1 cosine theta, so it's mg cosine theta minus 2mg and then plus 2mg cosine theta. If you want to simplify, because the minus will make it plus. And then last is you have 2mg plus theta. It's going to be 3mg cosine theta minus 2mg. And that's going to equal your normal force. Okay. Now, what angle at which a block loses contact with the sphere? Well, that's going to happen when the normal force goes to about 0. So this is about 0. So that means 3mg cosine theta minus 2mg is about equal to 0. So the mg's can cancel here. And you end up getting cosine theta is equal to 2/3. And theta is going to be inverse of 2/3. And if you want to use a calculator, you certainly could. So it's going to be cosine inverse of 2 divided by 3. If you want an exact angle, that's going to be 48.2 degrees. Okay, so yeah. So the setup's super important, right? And just got to combine that with a circular motion. All right, so block of mass m starts at rest point A, travels with negligible friction through the loop onto a horizontal surface, where the block makes contact with the spring of spring constant mg over 2. So we have a k mg over 2r. All the motion of the spring is in a horizontal direction. Point C is the highest point in the loop, and point B is the rightmost point. Express all algebraic answers in terms of m, h, r, and physical constants. Okay, derive an expression for the net force at point B. So what are we going to start with? Free body diagram, right? So this is going to be mg. And then what is it going to exert here is going to be a normal force on this direction, perpendicular to the surface. That's our rules. And that's pretty much it. So we're going to start with our free body diagram. That's that. And then we're going to say, well, we do F net equals ma. So in the x direction, we'll say left is positive and down is positive. In the x direction, when I do F net equals ma, we'll have the normal force is equal to m. Now, what kind of acceleration are we experiencing? A downward and a leftward. The leftward is centripetal acceleration, right? And in the y direction, you're just going to have, when I do F net equals ma, you're just going to have mg equals m and the tangential acceleration, the downward acceleration. So that's just going to give you the tangential acceleration is here, and here's the centripetal acceleration. All right. We need to figure out what that centripetal acceleration is, right? Because I know one of the components, but I need to know what the v is, and that's where we're going to use energy. So I need to know how fast he's moving at this point to figure out this component of the acceleration, right? And that way, if I know that, I can figure out Fn, and then I know this is mg, I can figure out what Fn is, and then I can do Pythagorean theorem to then calculate the net force at B. This is for the magnitude, by the way. This should have been stated. So let's figure that out. So how do I figure out how fast he's moving there? Well, that's where we're going to use work and energy, right? So system is going to be the Earth, because there's a change in height, plus the block, or block, right? And so we want to do our work. The normal force is not going to do any work because it's always going to be perpendicular to the displacement, right? And gravity doesn't do any work because it's internal to our system. So the work is 0. So therefore, we can do conservation of energy. So what is the energy we have here? Let's make down here h equals 0. So we have some gravitational potential energy, but we don't have any kinetic energy, right? How about the energy at point B here? All right. Well, we have some kinetic energy, and we have some gravitational potential energy because he's not at h equals 0. He's r above the ground, mgr. Right? So by conservation of energy, the mgh is going to equal 1/2 mv squared plus mgr. Notice that the m's can cancel. We can solve for v squared by doing gh minus r. You're going to subtract that over times 2. And that's going to be our v squared, which then that allows us to figure out our normal force, which is mv squared, which is 2gh minus r over r. And then the force of gravity is mg. So our net force is going to be square root of the x component squared to find the magnitude of the y component squared. So that's going to be square root of this squared. So it's going to be 2mg h minus r over r, all of that squared, plus mg squared. Right? So that's the net force there. And you can just leave it like that. You could simplify it some if you want, but that's fine. Just leave it like that. Derive an expression for the maximum compression of the spring. So now let's add in to our system the spring, because the spring is going to exert a force. As we come over here, we're going to exert a force from the spring. And if I don't include the spring as part of our system, it's going to do external work on it. So the work is still 0 now. And so the change in energy is 0. So we're just going to talk about the energy we start with. Now you could do here or here, but energy was conserved, so it don't really matter. Let's just start with that. The spring's not compressed at this point when the block's up here, so there's no spring potential energy. And at the end, well, once you're at the max compression, the velocity is 0. Because if it were still going, then that's not the max compression. So at the max compression, it's got to come to a stop because it's not going to go any further. So there's no kinetic energy. There's no gravitational potential energy because it's at h equals 0, so there's only spring potential energy, right? And so then we just set them equal to each other because the work was 0, right? This is mg over 2r because they told us what the spring constant was. The mg's can cancel. You can multiply by 4. You get 4hr equals x squared. So x is going to be square root of 4hr. Like that. All right, now suppose there's some friction cause a loss of energy as the block slides. How much energy could be lost for the block to still make it around the loop without losing contact with the track? Okay, so now now the work isn't zero. We definitely have a loss of energy here. Okay, so if we think about our system, the work is the negative work done by friction, right? And that's going to give you the final energy minus the initial energy. So the initial energy is still the same. It's mgh from our system, right? So we're starting here. And then now we're talking about the energy at point C. Now, what's the energy at point C? We do have some gravitational potential energy, and we're going to have some kinetic energy, right? So there at point C, final, which is the energy at point C, we're going to have some kinetic energy, and we're going to have some gravitational potential energy because we are now 2r above the reference height. The distance from there to there is that. And the spring's not compressed, so we don't have to worry about any energy in the spring. Okay? So how do we figure out that kinetic energy, though? Right? Like, because we're trying to solve for this guy. So we need to know what this quantity is. And it's not the same speed at B, because before we solve for the velocity at B, we need to solve for the velocity at C now. And we're going to do the same thing. We're going to draw our free body diagram. So at point C here, if we look at our free body diagram, we have mg, and we have a normal force, and nothing else is touching it. And at that moment in time, let's just pretend there's no friction. There was just friction on the ramp. So we have acceleration towards the ramp. So if I do F net equals ma, this is how we found the velocity before. We did the normal force is downward, make down positive, mg is positive, and that's m times the v squared over r that we care about. Now, when we're about to lose contact with the track, so the Fn is not exactly 0, but it's very close to 0 when we're about to lose contact with the track. So that's going to go to 0. M's cancel then, so the v squared is just going to equal gr. So then we know what this v squared is. So we know the final energy is going to be 1/2 m gr plus 2 mgr. That's going to be 3 halves. No, not 3 halves. 5 halves mgr. And then the initial energy. So the negative work done by friction, which is the final minus the initial, is 5 halves mgr minus mgh. Okay, so the work done by friction, so the work loss, you just multiply by -1. It would be -5 halves mgr plus mgh. So you're going to start with this, you're going to end with that, and the difference is how much you lost. Okay, so this is just the energy lost. Okay, so you can think of it that way. The energy lost. The energy lost is the amount of negative work that was done by friction, right? Okay, let's do one with some planetary gravitation. So if a spacecraft mass m is launched vertically from the surface of a planet, so this is m of mass m and radius r, with an initial speed v0. The gravitational force from the planet acts on the spacecraft as it moves away. So it's going to launch with some initial speed, and it's just going to head out. Okay, and then it's going to come back down because the gravity is going to eventually pull. Assume the initial speed of v0 is increased while keeping m and r the same. Will the maximum height of the spacecraft above the planet's surface increase, decrease, or stay the same? So basically, from an energy point of view, right, our system's going to be the planet and the mass of the spacecraft. When we start with more kinetic energy, we're going to end up with more gravitational potential energy for the maximum height, because here the velocity is 0 at the maximum height. Right? That's what we remember from kinematics, max height, velocity 0. So we're going to convert it all into gravitational potential energy. So it's going to increase because if you have more initial kinetic energy, will allow for greater maximum gravitational potential energy, right? Because remember, the higher we are, the further we are away, the more gravitational potential energy is. We want to derive an equation for r max the spacecraft reaches from the planet's center in terms of m, r, v0, and fundamental constants. So let's talk about the system. System's going to be, right, the spacecraft plus the Earth, because there's a change in height. Now, if we think about only the forces acting on it, is we just have gravity acting on it as we're moving. And that's not going to do any work, so the work is 0. Why isn't it do any work? It's part of our system. We've included the Earth. So we need to think about the initial energy. Now we got to think about, well, there's some gravitational potential energy, because when we use that planetary gravitational potential energy, we have to talk about not just V0 squared, because we're not saying H equals 0 here. When we use that gravitational potential energy for planets, we use the idea that infinite distance is where H equals 0. So there's some gravitational potential energy, G, mass of the planet mass, and the distance is he is away from the center, is R. Now the final energy, we don't have any kinetic energy, but we do have gravitational potential energy, but the distance now is R max. Okay, so we don't have any kinetic energy because the velocity is 0, but we have some gravitational potential energy because we're further away. And now we're just going to set them equal to each other. Minus G by conservation of energy because the work was 0. Big M, little m over R max. A lot of ways you can do this. You can multiply by R max and divide it over here. So I could just move R max is going to be negative G big M over little m. And then divide this whole thing over 1/2 m v0 squared minus G big M little m over R. Now the little m's can kind of cancel. So I would leave that. I would do that just because it allows you to see that it's not going to depend on how massive the object is, right? Now, you might think like, oh, should this be a negative number? Well, there's a negative sign, so the numerator is definitely negative, right, because of that. It turns out the denominator is also negative because this thing is going to be, it turns out this guy will be bigger than this quantity here, in all likelihood, as long as it has some velocity to leave. But yes, that would be true. Okay, does your equation for part G from part B, I don't know. For R, this should say R max. For part B, agree, right? So let's strip out the negative sign, right? So divide the top and bottom by negative. It's going to be GM over R minus 1/2 V0 squared, like that. And then what we're going to say is as we increase V0, as V0 goes up, this thing, the denominator gets smaller. So yes, because as V0 increases, then the denominator, GM over R, minus 1/2 V0 squared decreases, which increases R max. Okay, so that's the justification. Now you might notice like, hey, what happens when it divides by 0 here? What happens when this occurs? This is just a side note. This would, if you solve for this V0, it's 2gm over R square root. This is called the escape velocity. This is the amount of velocity you would need to launch it, and it never returns back to Earth. As long as you hit that speed, just go on forever. Right? It will go to infinite distance because you'll be dividing by a number closer and closer to 0. So then it will travel to an infinite distance. Okay, the last thing we want to talk about for working energy is the internal energy of a system. So when you look at a closed system, we sometimes talk about the internal potential energy. In a closed system, we talk about conservative forces. That is not a fancy word of saying that like all the internal forces just convert kinetic energy to potential energy. So if there's any internal work on the system, this is very different than the external work we did before. All the stuff we did before is about external work done by outside the system. But if you have a closed system, we're talking about internal work. Internal work is eventually conservation of energy. We are simply converting from potential energy to kinetic energy. That means the kinetic energy plus the potential energy is constant. So when we have work, internal work, it might cause a gain in the kinetic energy, but a loss in the gravitational potential energy or vice versa. So that's why there's this minus sign in here, as any internal work is going to increase the kinetic energy, but then if it's positive internal work, it's going to increase the kinetic energy, but then decrease the potential energy of the system. So there's a minus sign there. The total energy is remaining constant. And so if you want to look about what that internal force, or sometimes called the conservative force, aka conservative force, then the differential form is just, you just take this is the integral form, the derivative, you just say the f, if you take derivative of both sides, you get negative du dx, okay? Last thing to note about here is there's something we call equilibriums, is where the net force is, or the slope, so this is about the slope of a u versus x graph, because remember derivatives are slopes of tangent lines, is the internal force, that conservative force. So if the net force is 0, that means the slope of that graph is horizontal. You can have stable equilibriums. This is kind of like bottom of a bowl, because what ends up happening is if you move to the right, okay, the force actually acts to the left because the slope is positive, but then with the negative sign, the force will point in the negative direction. And then if you go in the negative direction, the slopes are negative, but the force will be positive. So the force will always bring you back to this equilibrium position here. Whereas an unstable equilibrium on the force on this graph, this potential energy, if you look at it as potential energy versus x graph, right? You have an equilibrium here where the tangent line is 0, right? So this is equilibrium. But if we go over far enough here, we have negative slopes, right? But with the minus sign, negative means it's a positive force, so the force is going to point this way. That means once you get off this equilibrium, it's going to just keep going off of it. So this is called the unstable equilibrium, because if you just teeter off the edge, it's just going to kind of roll away. So sometimes people think about this potential energy graph as like kind of a ball rolling on a hill or something like that. So this is a stable equilibrium. This is an unstable equilibrium. So let's go through an example of a problem here. So we have small object of mass m moves along a frictionless horizontal line under the influence of a conservative force. Potential energy associated with the object is given by this equation here, where this is true. General sketch of the potential energy as a function of x is shown here. Express all your answers in terms of a, b, m, and c. The objects are released at rest from x equals x0 and moves under the influence of the conservative force. Determine an expression for the minimum value of x0 such that the object continues moving forever and never turns around. Express your answers in terms of here. So we're going to release it, okay? So that's a velocity equals 0, so there's no kinetic energy. So it's going to start at some point. Like let's say we did it here. What's going to happen is it can't exceed this amount of energy, because this is u versus x, right? So like the total energy is going to stay down here. So it's just going to oscillate between here and here. So if we want it to never go back, we want to say how much energy is it down here. So we want to look at the energy. First, we want to know what the energy is at infinity. So we're going to do the limit, x goes to infinity, of this expression, negative ax minus b over x plus a squared. Now remember, with limits at infinity, we just keep dominant terms. On the numerator, the constant term will go away, and that will go away as well, because x will get bigger and bigger. So this is going to be negative ax over x squared. That's going to cancel, and as you go towards infinity, this is going to go to 0. So this is going to be 0 joules of infinite energy down here, okay? So when you're infinite distance, the potential energy is 0. Now, in order to have a potential energy of 0 energies, we have to start with at least 0 joules of total amount of energy, right? Because we just assume here that the velocity is 0. If the velocity were faster at infinite distance, it would have some kinetic energy. But at a minimum, we need 0 joules of energy in order to make it all the way that far and have 0 kinetic energy left. If we have any extra energy, it would turn into kinetic energy. But at a minimum, we need 0 joules of energy. You might think like, well, don't you always have 0 joules? Well, potential energy can be negative, so not exactly. So if we release from rest, so our initial energy has to be the sum of the kinetic energy plus the potential energy, and this needs to equal the final energy, which is 0. Okay. Now we're releasing at rest, so we want to know when do we release it to where the potential energy is 0. Now you can say, well, infinite distance it'll be 0, but we're not releasing it from infinite distance. We're releasing it somewhere here. So we know when this quantity x plus a squared is equal to 0, and that's just where the numerator is 0. So we have negative ax is equal to b, so x is equal to negative b over a. And that would be the point, and that's going to be our x0. Okay, so we just solved for when the potential energy was going to be 0. So that's going to be like, let's see, I plot this correctly? Is this supposed to be ax minus b? But it's going to be somewhere, around here. Now, why is it negative? I think this is supposed to be ax plus b. I think I made a slight typo in there. In the setup, so it's supposed to be positive b over a, because I think when I graphed it, it's ax plus b actually. Okay, so we're just effectively finding when it's 0, because then at infinite distance, it will have 0 potential energy as well. Okay, determine the magnitude direction of the force as a function of x. Express your answers in terms of here. So F is equal to negative du dx. And remember, our u of x, we're going to say is negative ax plus b over x plus a squared. So we're just going to take the derivative of that. Just do quotient rule if you want. So do bottom. So negative, and then we'll do bottom times the derivative of the top is going to be negative a minus top times the derivative of the bottom, which is going to be 2x plus a, divided by bottom squared, which can be x plus a to the fourth. Honestly, you could just leave it like that. You could simplify if you want to do some of these things. But let's make this negative. This is going to be negative a x squared plus 2ax. Well, let me just see if there's any worth of combining any terms you can think about. Minus... yeah, I mean, I honestly would leave it like that. You could, okay, there's a couple of things you could do. I mean, so this is fine mathematically, just as long as you know how to compute the derivative. That's really all I wanted to test. But you can do things like you could factor out an x plus a, because you have one on the top. So this would be negative a times x plus a. And then minus 2 times negative ax plus b, because you pull out this x plus a, over x plus a to the fourth. So you can cancel one of those out and make this cubed. Right? So this is going to be negative, and then negative ax minus a little a, and you can make this plus 2ax minus 2b over x plus a cubed. Only if you want to simplify this. You don't have to do all of this work. You could distribute the minus sign if you wanted to. Put that minus sign through everything, so it's going to be ax minus 2ax, then plus a plus 2b over x plus a cubed. Okay, so I'm just showing you a few things you can simplify. You honestly don't have to bother with doing that. Simplifying can be helpful if you're asked to interpret if something increases and things like that. So that's the only advantage of sometimes simplifying. Let the object released from rest of position x1 where x1 is less than x0 from part B. Determine the kinetic energy it will have as the object goes an infinite distance away. Express your answer in terms of this. So now we're going to have some potential energy. So our initial energy is we're going to have some potential. We're going to have energy here. And our final energy will have our potential energy at infinity plus the kinetic energy. We already said that this is 0. So the kinetic energy, because the energy is conserved, is just the potential energy at x1 is going to be what our kinetic energy is. Okay, so that's just going to be plugging x1 into this expression. So it's going to be negative ax1 plus b over x1 plus a squared. And so but again, that's just what you want to think about. You want to think about what energy do you have at the start, how much energy do you have at the end, and conservation of energy. And you just want to think about the total energy being constant when you're looking at a graph like that.